All right, good morning. Welcome back. Advent of Code, day 9. Let's hit it. Oh. Welcome back. Advent of Code, day 10. Let's get it done. Boom. All right, patched into aircraft's data port, you discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared, you make a list of all of the joltage adapters in your bag. Each of your joltage adapters is rated for a specific output joltage, which is your puzzle input. Any given adapter can take an input, 1, 2, or 3 jolts, lower than its rating and still produce its rated output joltage. Can take input joltage lower but still produce its output joltage. In addition, your device has a built-in joltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. If your adapter list were 3, 9, and 6, your device's built-in adapter would be rated for 12. Treat the charging outlet near your seat as having an effective joltage of 0. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to get to your resort and realize you can't even charge your device. If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? I don't understand the question. For example, suppose that in your bag you have adapters with the following joltage ratings. 16, 10, got it. Looks like it goes from 1 to 19. With these adapters, your device's built-in joltage adapter would be rated for 19 plus 3, so 22. 3 higher than the highest rated adapter. Because adapters can only connect to a source 1 to 3 jolts lower than its rating, because adapters can only connect to a source 1 to 3 jolts lower than its rating, in order to use every adapter, you need to choose them like this. Oh gosh. Here's an explanation of the algorithm. The charging outlet has an effective rating of 0 jolts. So the only adapters that could connect to it directly would need to have a joltage rating of 1, 2, or 3 jolts. Of these, only one you have is an adapter rated 1. From your 1 jolt adapter, the only choice is your 4 jolt. From your 4 jolt rated adapter, the adapters 5, 6, or 7 are valid choices. However, in order to not skip any adapters, you have to pick the adapter rated 5 jolts, difference of 1. Similarly, the next would be adapter rated 6 and then 7 with a difference of 1 and 1. The only adapter that works with the 7 jolt rated adapter is the one rated 10 jolts, difference of 3, 10 minus 7. From 10, the choices are 11 or 12. Choose 11, difference of 1, and then 12, difference of 1. After 12, only valid adapter has a rating of 15. 3 difference, and then 16 difference of 1, and then 19 difference of 3. Finally, your device's built-in adapter is always 3 higher than the highest adapter, so its rating is 22. Always a difference of 3. In this example, when using every adapter, there are 7 differences of 1 jolt and 5 differences of 3 jolts. Here's a larger example. In this larger example, in a chain that uses all of the adapters, there are 22 differences of 1 jolt and 10 differences of 3 jolts. Find a chain that uses all of your adapters to connect the charging outlet to your device's built-in adapter and count the joltage differences between the charging outlet, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? Okay. This is a real weird one, guys. So, This is so weird. Okay, so I'm gonna really quick here. I'm gonna do an extension on string that is called it's called ints, and it gives me an array of ints. Again, something that I would only do in a coding challenge because we do this so often. So it seems like a good opportunity to take advantage of this. So first of all, this is so dumb. First of all, these are substrings, and then substrings need to be converted to ints, not exclamation mark. Okay, so what we're going to do is we're going to say num equals input.ints. What? Does two? I just create, oh, string.subsequence. Whoopsies. Wrong thing. Okay, so we've got our numbers. And then what we're going to do is we're going to do numbers.sorted.sort. What does it sort it by? Elements are sorted in ascending order. Okay, sounds like what we want. And then just go through and count the differences between each one. I mean, that like sounds really easy. Var 1 jumps equals 0, var 3 jumps equals 0, and then I in 1 ... less than numbers dot count. Cause like, that's fine. If numbers sub I, which would be the larger one, minus, let's see, we want diff. Numbers sub I minus numbers. So what we're doing is we're taking this just two numbers at a time after they're in order, because like based on how they described it, that just sounds like all you're supposed to do is just put them in order and then get the difference. And then if diff equals 1, 1 jumps plus equals 1, else if diff equals 3, 3 jumps plus equals 1. And then you have adapters. With these adapters, your device's built-in voltage adapter would be rated for 19 plus 3, which is 22, 3 higher than the highest rated adapter, because adapters can only connect to a source 1 to 3 jolts lower. Okay, and then it's just, okay, so, and then we get to the end and we print 1 jumps, 3 jumps, and 1 jumps times 3 jumps. Seems weird. But that's what it seems like it's supposed to do. 6, 4, and 24. There are, in this example, when using every adapter, there are 7 differences of 1 jolt and 5 differences of 3 jolt. It's 7 differences because the lowest one is 1, right? Okay. So weird. So plus 0. Well, yeah. And then 3 jumps is always going to have 1 more than it because the last number is always 3 higher. What a weird question. So 7 and 5, is that what we're supposed to have? 3 jumps. Okay. Very weird. Let's do a larger set here. Boop. Make sure we didn't get any weird. We did get a weird white space. Okay. And then with this larger one, it is supposed to be 22 and 10. 22 and 10, which is 220. Okay. It sounds like we're doing what it's asking. It just feels weird, is all. I messed up the white space again, as always. 30, 34. I'm just saying it feels weird because it's like, it's the rules that you're following are kind of random and arbitrary, but like, and the like solution, like it sounds like it's describing something much more complex than it actually is, which is just sort the list and then count the difference between each of the numbers. Anyway, let's keep going. To completely determine whether you have enough adapters, you'll need to figure out how many different ways, there it is, okay, how many different ways they can be arranged. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. The first example above, the one that starts with 16, 10, 15, supports the following arrangements. 1, 4, 5, okay, so it always has 0, 1, 4, 5, or 6, or 7, okay, got it. Supports the following arrangements. The charging outlet and your device's built-in adapter are shown in parentheses. Okay, so I'm also going to do this really quick. And then numbers plus, or I guess I can just do append numbers dot last plus 3. And then that should give us the exact same result as before, 74, 41. Okay. So this is the same thing, but it more accurately reflects what they're asking for here. Okay, the charging outlet in your devices are shown in parentheses. Given the adapters from the first example, the total number of arrangements that connect the charging outlet to your device is 8. The second example has many arrangements. Here are a few. In total, this set of adapters can connect the charging outlet to 19,208 distinct arrangements. You glance back down your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways to arrange them. Surely there must be an efficient way to count the arrangements. What is the total number of distinct ways you can arrange the adapters? Okay, here's the actual hard problem, and I'm guessing that like if there's legit 1 trillion ways, we might be in trouble. What is, whoops, didn't mean to refresh that. Where's the page? 64-bit int max. What is it? Which is 1,000 million billion trillion. Yeah, we're good. I just didn't know if that was like, I'm guessing that like this is supposed to like trip up people that are using a 32-bit system or language that only has their ints are only 32-bit by default. Maybe since its warning is very clearly that there's 1 trillion options. Okay, so the question here is, how many combinations can we possibly have? Okay, we are now going to skip ahead back to the struggling solutions. Now, if this is something that you want to see, you want to actually see me go through some of these iterations and struggle with these other solutions, keep watching. I think that it's kind of interesting to see that solution play out, but that is not the solution we end up keeping. Or to which ones can it jump ahead to, and then just count the number of, there's probably like some sort of multiplication that I can do. So So this is going to be churning for a little bit. So let's play with the initial input for a second here and see if I can okay, so 0, 1, 4, 5, 6, 7, 10, 11, 12, 15, 16, 19, 22. So in this case, we can look and say no jump aheads, no jump aheads, no jump aheads, can't jump ahead. This can jump ahead. Nope, it can't either. This one can't either. Right, 11 to 15. This one has one jump ahead, one way that it can jump ahead. 7 has 0, 6 has 0, 5 has 1, 4 has 1 and 2, 1 has 0, so 0, so 2, 3, 4, 4 ways that we can jump ahead. So how can we can basically say, like, okay, we always know that there's one way forward. We know for sure that there's one way forward. So we get to the end, right? We know that that's one possibility. But then we know that for every answer after 10, there's 2 ways forward, right? So this takes it from 1 to 2 paths. So there's now 2 paths forward to finish. There's 1 path forward to finish. This, because there's this introduces 2 paths forward from here, which means that this is 2 times 2 is 4, which means that this becomes four paths to finish, right? Because and then this, because there's 2 jumps, but there's 3 paths, right? So that means that there's 3 paths forward. So 3 paths, and then 3 paths turns into 6 paths, because each of those 3 split twice. And then 6 hits 2 paths forward, which would become 12. So that's still not right, because the answer for part 1, or for this, is 8. There's 8. But there's something to this, I think. So let's try this again here. I'm gonna, to save myself some time, it's this one, and this one that can branch. Okay. So, yeah, 10 can skip 12, right? 10 can skip to 12. Yeah, 4 can skip to 6 and 7. 4 can skip to 6, 7, and then 5 can skip to 7. Okay. So going through 10, there's 2 paths. They go through 10. I guess there's, what I actually want is there's one path forward for each of these. So it's always one, and then it hits 2, which means, which means that if we hit 2, that means that there's 2 paths through 7 as well, right? Because basically it splits backwards, kind of branching backwards, I guess, which means that since there's 2 paths, there's 2 paths through 5, which means that there's actually 4 paths, and then there's 3 paths through 4, because 4 can go to 4, can go to 5, it can go to 6, and it can go to 7, which then brings it to 8. Like that's the weird one, which brings it to 8 paths. So I mean, like that, it's like for every index that branches, like, yeah, I guess in theory, for every index that branches, like in theory, like this one makes sense, right? 2 times 1 is 2. This one makes sense because there's 2 paths forward, 2 paths forward, 3 paths forward, right? So 1 times 2 is 2. 2 times 2 is 4, but 4 times 3 is 12. So that's the one that's throwing me for a loop. Like, why aren't there 12 paths that go through 4? Because not all the paths that go through 4 go through 5. So it's not 8. It is one of the paths goes through 5. So it is 4 plus 2 plus 2 plus 2, which is actually 8. 4 plus 2 plus 2. Is that right? Because what this actually is 10 can go through 11 or 12. And then 5 can go through 6 or 7, so 4. And then 4 can go through 5, 6, or 6 or 7, which is 8. I kind of want to let this keep running just because it's already run for so long. But at the rate it's going, I actually don't know how long it would take it to finish. So let's kill it. Let's try this other solution here. So, if we count backwards, how do we determine so what we're actually counting is how at each location, assuming you can make it to the end at each location, how many of the following are valid jumps. Let's try that really quick. So, man, that would be hilarious if that's what we're doing. If diff is less than or equal to 3, var valid jumps equals empty. I'm gonna is there an event? So what I actually want to do is I want to go through each one and say why does it can I assign? Okay, sorry. So what I actually want to do here is I want to go through and I say for each index, I'm going to count forward again, minus 3, I guess, technically, or minus 1, and then what I'm going to do is I'm going to go through each one, and I'm going to say, okay, let diff is I plus 1, diff 1, diff 2, diff 3, diff 2, diff 3. So I'm actually trying to count is for j in I less than I plus 3. So 0. I plus 1 through I plus 3. And then I'm going to say var jumps equals 0. I'm going to count the number of jumps that are valid. So if numbers sub j minus numbers sub I is less than or equal to 3, then jumps plus equals 1, else don't check anymore. And then valid jumps dot append jumps, and let's just print valid jumps with the small sample input and we'll also do the medium sample input afterwards. And let's make sure the valid jumps actually looks like our spreadsheet here. Okay, 1, 1, 3, 2, 1, 1, 2, 1, 1, 1. Okay. So basically, what we end up with here is, so then we're going to step backwards through this, and we're going to say this this one, the total number of jumps is this number added to nothing else. There's just this number, is just this number, is these two numbers added together. Okay. Paths are paths. Okay, and then we're going to say for jump in valid jumps dot count minus 1. Let's see. I want in stride from valid jumps dot count minus 1 to 0 by negative 1. I think that works. Yeah, so that'll step us backwards. And then we can say, I think we actually want minus 2 here. So because this one doesn't have anything to look at. That's That's just the answer. So what we're going to say is we're going to say paths equals, okay, whoop. Let look ahead equals valid jumps sub jump. This is an index, it's not a jump. Index. And this is jump. Okay? And then what we're going to say is at each of these indexes, we're going to look at that many things. So var count equals 0 for j in jump. Let's see, in index index through index plus jump. Count plus equals valid jumps at j, and then paths equals count. I'm sure this isn't perfect, but it feels close. Okay, so the first jump is a jump of 1. So count is 1. Count is 2. Let's try it again. Okay, it is looking at j, which is 8. Zero, 1, 2, 3, 4, 5, 6, 7, 8. What? Valid jumps only has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, because we didn't bother going all the way to the end. Which is probably fine. That's probably fine. We can just say, okay, there's no skip aheads. So count is 1. So valid paths. So paths equals 1. Valid jumps. What does count equal? I'm gonna do it from here. Count equals 3. Did we hit here? Paths equals, or count equals 3. Valid jumps. What did we just look at? Index. Index is 6. 2. Index plus jump. That doesn't feel right. Plus jump is 8. So look at 7 and 8. Add those up is 2. Index is 6. 6, 7, and 8. That's not what I want. I want x plus 1 all the way through. I think that's what I want. Okay, so the first time we hit this, we are looking at count. Count is 1, good. Count is 1, good. Count is 2, 2, and then 2, count as 1. What am I at? I'm at index 4. Because I'm just looking ahead at 1. So this one, I need to like back populate. Or count. Do I need to count backwards, count forwards? So what I need to do is I'm trying to build this, or I'm trying to build this, right? So I guess I can't. Because this look ahead is telling me what I need to look for in this array, and this array needs to actively change. So can I count forward though? So I'm adding, right? So I'm looking at these 3 and adding them together. So what this actually needs to be is look at 1, 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 look 2 ahead and add them together. This would be 1 and 1, but what I actually need these to be is oh, so I guess technically what I'm doing is, so these are all 0. No, because then that doesn't work either. So this is looking at these 2. It's every time the numbers if the number of valid jumps is more than 1, then I actually add it. If not, I just keep the previous. I just keep the previous. So this is add these 2. This one though, this one is, yeah, I feel like I need to switch these. So I'll look at these 2 paths forward. This one, I look at this one, and there's still 2 paths forward. I guess technically what I should be doing is this one looks at these 2, and that's 2 paths forward. This one looks at this one, 2 paths forward. This one looks at this one, 2 paths forward. This one looks at these 2, 4 paths forward. This one looks at these 3, 8 paths forward. This one looks at this one, 8 paths, and this one looks at this one, 8 paths. Okay. I guess that's really what I'm supposed to be doing. Okay. Paths is an array of integers. Equals array, is there fill? Repeat. repeating, good enough, count valid jumps dot count. And then what we're going to do is we're going to say this is in, and then the number is actually paths sub j, and then path sub I sub index equals count, and then print paths. Which is 8. This is interesting. So 1, why didn't the last one? I'm just curious to try it with the longer input, just because this video is already so long. We're gonna paste this here and see what it does with the longer input. J is 30. J is 30. Paths has 30. What? Index is 28. Valid jumps 28. So it does 29 and jump of 3. How did we get a jump of 3? A valid jump of 3? That's not right. Let's print out our numbers then. Do I have a bug there too? A jump of 3 on this last one. 49. How do I have a jump of 2 on the last one? For J and so my valid jumps are wrong now too. 0 can 1, 2, or 3. So that's right. 1 has 3 valid jumps. And then what? PO valid jumps dot count, PO numbers dot count. Oh, okay. So it's not 33, it's 47, can go to 48 and 49. Okay, and 46 can go to, okay, so this is -3. No, still not. Trying to get into index J again. Index is 27. 27 has 3 jumps. There's 33 numbers. There's 33 numbers. There's 30 valid counts. Valid jumps. j is greater than or equal to paths.count count plus equals 1 else. So it's because we're short-circuiting early, we don't have the padded ones at the end. Was 220 the right answer? Five differences, here's a large number, 22, 10, paths, 4,704. This large example changes all the way up to there are 22 differences of 1, 10 differences of 30. So it's supposed to be 32. Three. Okay, well, thanks for letting me take a break. Let's talk about what I did right and what I did wrong here. We actually we were doing it right. We really were. The problem that we were running into, or conceptually we were doing it right. The problem we're running into here, let's take a look at, this is what we had, and this is what ended up working. So, first of all, we were going through and calculating all the valid jumps. In fact, let's do this really quick. Let's uncomment this. Let's uncomment this and show you. So, oh, this is my full input. So we were actually going through and calculating the valid jumps and then putting those in an array. And okay, welcome back. Thanks for letting me take a break. Solved it. Turns out sometimes you just need to walk away and it kicks your brain into gear. You figure out what's going on. So if you actually take a look, we were doing it correctly conceptually, where we were calculating all the valid jumps. So let's show you that really quick here. So we were calculating all the valid jumps, which is good. Got that right down here at the bottom. And you can see the jumps range between 3, 2, or 1 possible jumps. And we even had this part right where you were, basically saying, okay, well, at this point, we need to look ahead. The problem that I had, and I don't know why I couldn't see this, is you need to be populating as you go. So what that actually means is you kind of don't actually need this valid jumps array. You calculate them as you go. So in this case, there's only one valid jump, one valid jump, one valid jump, and it keeps going. This one, there's 2 valid jumps, so you add up these 2 together. And this one, there's 1 valid jump, so there's 1 valid jump right there. So you just add this one, 1 valid jump, so you just added this one. This one, there's 2 valid jumps, so you add these 2. And that was it. So I don't know how I wasn't seeing that we were doing that wrong, but you can see we're calculating the valid jumps correctly. So basically what I did was I took this part. I more or less did the same thing here, right? I created an array of valid jumps. The only thing I did was I just filled it with 1 to make sure that it indexed correctly. It indexed the same as the numbers array. And then the rest is basically the same-ish. So this is the same except for I changed it to J in 1 through 3 rather than I plus 1 through I plus 3, but literally ends up being the same thing. If it's valid, then you add to it, otherwise break. Okay, like literally the same thing here. So this part of the array was good. The problem is we were always looking at, we were always summing up and just saying, oh, jumps plus equals 1. So this was counting the jumps, but we weren't looking at the total. We don't want to know the total number of jumps. We want to know the combination of the previous possible number of paths. And so in this case, like we literally just said, there's 2, so you want to look at the previous 2 and add those up, not just 1 every time, if that makes sense. And so then all of this nonsense about going back through and trying to populate a new array, which you can see, right? We stole this part right here and put it right here. This whole thing about going through it and walking backwards and pulling stuff in and would never work, because you need to be backfilling as you go so that you have updated values. And that's where I was stuck, is trying to figure out how to get those updated values. So the crazy thing is, if you want to see the actual final result here, and how fast it runs compared to the several minutes that the previous solution was taking, that's it. Done that fast. Which hopefully, gives you an idea that in this case, 2 lessons. One is if you look at the way that the problem is slated. I was concerned from the beginning that it said more than 1 trillion valid ways. That immediately is concerning, right? Like when you start hearing more than 1 trillion valid ways, that should trigger in your mind, hey, don't brute force this. So I shouldn't have wasted so much time doing this. In fact, I'm going to cut this and make this make more sense later in the edit. But all of this was a waste of time, because yes, it's accurate, but it takes forever. So first tip, you see something like this in a programming challenge, this is tipping you off that there's some sort of pattern that you can use, and that you shouldn't just be going through literally every number and calculating every possible combination. So that's the first thing. The second thing here is that when I had the array, this list built up, that I was slowly saying, okay, well, it's 1, it's 1, it's 1, it's 1, it's 2, it's 2. That should have been obvious that this needs to be a single list that is backfilled. And I don't know why I didn't see it at the time, but that is another thing, is trying to accurately represent what we're doing. Because remember, that other solution was like jumping back and forth between these 2 arrays and trying to figure out like which one goes to where, and then putting it into this one. Never would have worked. So, I mean, probably because my brain had been spinning on it for an hour at that point. But there you go. There's the solution right there. All in one thing. You backfill as you go, and then you end up with the solution. Okay. Hopefully that was a valuable lesson for you guys. Again, even if you've been programming for a while, the solution isn't immediately obvious, and when you get in a hurry, sometimes you chase down the wrong solution, like I did, for way too long. So hopefully this is useful for you. Again, we're going to be doing this every day. We're going to be learning something every day. So if you enjoyed this, make sure you like and subscribe and share it with people so that we can keep growing the channel. But also, check us out tomorrow, because we're going to be doing this again and learn something tomorrow. Okay, thanks. So, what we want to do is we want to basically do the same thing we did. We want, basically the same thing, but we're going to do, I'm going to do looking ahead instead of looking backwards, just because mentally I think it's like easier. And And then we're not counting the diff. So what we want to do, var j equals I plus 1, while j, let's see, var joltage 1 equals numbers sub I, while j is less than numbers dot count. And so we're only going to look ahead at most 3 at a time, but how we're going to do that is we're going to say numbers sub j minus joltage 1 is less than or equal to 3. I think that, yeah, 10 minus 7, 3. Yeah, that's what we want. So basically this says, okay, we're looking ahead, and if the number we're looking ahead at is small enough, then that's going to be, then we're going to consider this as part of our joltage count. Okay. And we actually need to, so this would do it. I'm curious about this. I actually don't know the answer to this. If I look at each position and say how many possible following, well, because each of those creates a branching path. So there's probably some way that I can look and say, okay, this index supports this many possible, but they're dependent. Ooh, okay, so like the brute force way would be to like look at every possible branching path, and based on my input, I mean, it says 1 trillion. We'll see if that's actually true, I guess. So okay, let's just keep cruising on this. I don't know enough. I'm sure somebody's actually going to solve the answer the way I just described, but there's like some way that you can actually map the paths back to each other and like save yourself some effort. But trying to do it quickly, I can't think of what that would actually be, but I'm sure somebody's going to have a cool solution. If that's you, put it in the comments. If you find somebody that's got to put a link in the comments, I want to see it. Okay. So I guess what we're going to do then is we're just going to say, okay, well, we're going to say, I don't know why I made this a var. This can be a let. And then let joltage 2 equals numbers sub j. Okay. And then at the end of this, we're going to do j plus equals 1. So basically, we're going to start 1 more than I, and then we're going to do this loop on each number larger than I. Why is my white space wrong? That was very, very weird. Okay. So then what we're going to do is we're going to repeat this. So basically, we've started at I, and we're going to repeat this. We're going to file private func. Or is the trillion tipping me off that this is going to Stack Overflow? I guess we'll find out in a second. My brain just thinks better, I think, about recursive functions. So we're going to try recursive function first. And if it Stack Overflows, then we'll have to move it to a data structure. Okay, so all combinations, and it's going to have numbers, which is an array of int, and then it's going to have start index, which is going to be an int, and it's going to return an int, which is all the number of combinations. So in this case, what we'd do is we'd say print all combinations of numbers at start index, and we're going to start at 0. And then what we're going to do is this is for start index. This is numbers. Start index, numbers, joltage 2, and then we're going to say var count equals 0, and then we're going to say count plus equals all combinations of numbers and start index of j. Do we even need the, I don't know that we even need the joltage here. So then we just rinse and repeat for every one of these, and then we return the count. So let's play with the input that they started us with, the small input. The way, like the trillion has me a little concerned that there's going to be something that catches us about it. Okay. So what does it say? All of those arrangements supports the following arrangements: 1, 2, 3, 4, 5, 6, 7, 8. 8 arrangements. Oh, there it is. 8 arrangements. Okay. And then this one we don't need all of them. We just need them. 0. That's not good. Let's take a look and see what's wrong with this. Since okay. Oh, let's see. PO joltage 1, PO numbers sub j. That's 1. Yeah. Oh, wait. That is what I wanted, right? Yeah. I thought that would be the part that trips you up. Is less than or equal to 3, which it is. Oh, does this, and this needs to be +1 for this step, and then, okay, I think that's what it is right there, is you got to count the step that you're on. 8,319, that ain't right. Okay. Let's see. Count plus equals 1, because this is a, oh, it goes until it gets to the very end. It goes until it gets to the very end. And then count plus equals 1. Nope, that's not right either. So, okay, let's think about this for a second. I'm kind of curious. I want to see, looking at the stack, what so it goes from, or we went from I is 11 and J is 13. That's not right either. Yeah, that's not. Okay, I'm actually, I'm being real brain dead here. Okay, let's just step through like a normal person and see if we can understand. Okay, so we get 0 and 1, and then 1 and 2, and then 1 and then 2 and 3, 0, 1, completely turn. Oh, is this not doing what I think it's doing? 2 is 3. Oh, these are the positions, yeah? Or are these the numbers? Those are the numbers. Okay, I'm going to print joltage 1 and numbers sub j, because I still don't really understand the code that I've written, apparently. Okay, so 0 and 1, which is matching up, right? And then I guess I can just get to the end here. So 0 and 1, 0 to 1, 1 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 10, 10 to 11, 11 to 12, 12 to 15, 15 to 16, and then 16 to 19 and 19 to 22. Why did it? I don't know why it stopped. Oh, there it is. I just have to scroll down. 16 to 19, 19 to 22. Okay. Cool. Just need delimiter there. And then 19 to 22 again. 6, 7, 10. Okay. Okay. Yeah, they were right. There's a lot of combinations. I don't think this is right though. So 19 to 22, that's right. Hits the end, and then it hits the end again. Oh, okay. So I think what actually is going on here is, let's run it to prove this. I guess you're getting a lesson in how to use the debugger. Okay, I think what it's doing is it's hitting right here, which is one before, and then we're gonna step over, nope, step up and out. Step over, so J is 12, and numbers has 13. And then it immediately exits out and hits it again. So basically it steps in one's level, and then the next level exits again immediately, because this part of the condition is failing. It's hit the end of the array. It would be funny if I could just short circuit by saying -1, but I don't know that that's exactly what I want. I think what I actually want here is so what I actually want, what I'm trying to count is the number of times that I've made it to the end in a unique way. And in this case, I hit 19 and then immediately hit this again. Which is part of the problem. I mean, I guess I could. Is that actually the one that I want though? Okay, so this is what I want, all the way through 19 to 22, and now I'm looking at the index. I want this is because even if I do -1, that's still not quite what I want, right? Because -1, no, I don't need the joltage. -1 will stop me earlier. Yeah, that's definitely not what I want. What I actually want is on the iteration where there's nothing left to do. Which is actually, that's actually, let's run it again. That's actually how I hit this last one, right? Is you hit, stop. I actually, so how do I hit this one because, what? I never hit that one. Oh, I hit this because this one bottoms out, right? There isn't, okay. So that's why I hit this, is because it's like, oh, okay, you're actually at the end of the list. So if this for loop bottoms out, we know we're at the end of the list. If this one bottoms out, then we know that J has bottomed out. Does that actually work? That'd be a little hilarious if it did. And the end result is 121. Is that supposed to be? No, the number of arrangements is 8, but at least I'm closer, I guess. So 0, 19 to 22, I'm still hitting these two. I guess I can just print the count at each given point, because even though I'm going to hit it twice, like hopefully the count is at least accurate. Still 1. Okay, cool. So then it does 19 and 22 again, which is not unique. So that's a problem, but still at 1. Okay, so 16 through 19, and then 19 to 22. So 16 to 19, 19 to 22. Okay, so it's just slowly backing back out until 15, 16, 16, 19, 19, 22. So I can already tell my algorithms are inefficient. 19, 22, where does it actually hit the first additional? Because it just keeps stepping itself back out. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1, 1, 1, 1. Oh my gosh. Okay. Find star 2. Where's that finally happen at? 16 to 19, and then 19 to 22. Okay, is there a way I can make my life easier by actually printing this out instead? So this would be how they're searching is they're saying go all the way through all the combinations, but then they are printing out which one got cut out? 1, 4, 5, 6, 7, 10, 11, 12. 11 is the first one to get cut out. Actually, how do I even end up with 120 combinations? 121 combinations. Whoa. Oh, 1, and then 121, because it's finally coalescing all of them. Okay, so this is kind of doing the right thing, but clearly not exactly right. So what we want to do is we go through each and every one of these, and we say, we've actually already got this part right, and then it is checking each branching path. I'm actually, just to make my life easier, I'm going to do already visited, just to make printing this out easier. And then we're going to do already visited is already visited plus numbers sub j, right? Number sub I, and then did that wrong. Already visited is empty. So already visited is empty. We are starting at I. I has been visited. And then we're going to try every combination of I and numbers sub j. And then we're going to print out already visited. And then there's got to be a way to, like, I'll solve that in a second. Next up, I don't want to see that. Okay, so 0, 1, 1, 4, 4. Okay, so I don't need both. 1, 4, 5, 6, 7, 10. I actually I want to be able to see this. Okay. 1, 4, 5, 6, 7, 10, 11, 12, 15, 16, 19, 22. And then the next one is shorter. Okay, so I want to work this out instead of this stupid hacky count minus equals 1. Okay, so I guess what I can do is I can say if I is equal to numbers.count minus 1, I can just say return 0 and don't print anything. Sorry, not I, start index. So this is our reached the end situation. So that'll make it so that we don't do anything in the instance where we've reached the end. And that should help. 1, 4, 5, 6, 7, 10, 11, 12, 15, 16. Okay, but now already visited only goes to 16. And that's because the start index is 10. and the numbers is 13, and all combinations. Actually, let's do this. I think that hits this, boop, 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 and then it exits out. And then at that point, okay. So this works right the first time. I only want it to print out when it's actually reached the end. Which I guess is here, right? This is when it's actually if j equals numbers.count, then we want to print already visited, and then we want to increment the count, because I don't want to do any of that for the times that it's just it ran out of things to count but didn't actually reach the end of the list. No, it's still why would it still, so why does it still print? Because it didn't actually reach the end of the list in this case, right? Oh, it's not printing out 22. So these are, okay. Right, so that's actually what's happening. Already visited plus numbers.last, it's just not getting put on there. Sub number sub j, I guess. Wait, actually, so I guess I could just do this. Numbers.last would get me a more accurate representation, I think, of what's happening, but that still doesn't feel right. 1, 4, 5, 6, 7, 10. Good. And then 16 can't go straight to 22. 15 can't go to 19. Yeah, how did 15 jump to 19? So this is, so something is like actually just like actually wrong. Let's see. So every time we come around, we're going to print out numbers, sub j, and joltage 1. Let's run this. 1 and 0, 4 and 1. 1 and 0. Yeah, 1 and 0, that's the first error. 4 and 1, 5 and 4. 10, 7, 11, 10. I should have printed these in the other order. 12 and 11, 15, 16. 12 and 11, 15, 12, 15, 16. 19, 16, 22, 19. Okay, good. And then 22 and 19 again. And then 19, 16. Which is valid. And 22, 19, 22, 19, 15, 16, 16 to 19. Okay. Is there a way, I want, this is already so messy. Is there a way that I can bail out and say, okay, 1, 4, 5, 6, 7, 10, 11, 12, 15, 16, 19, 22. Got that. That's the first recursion. That works. and then say, okay, don't do anything more. Like jump all the way back to 11. Like 11. Just got startled, baby knocking on the door. Like, is there a way that I can say, okay, jumping from 10 to 12, that is the actual thing that I need to go back to. I need to go back to the first instance where I could skip. Because this is getting to be a mess real quick. Because in theory, what should happen is the way my loop works is start at this one, look at this one, and then repeat the branch. So start at this one, look at this one, start this one. But the problem is that we also get a pile of 16, then has to look at 19 and 22 and see if we can just skip, which actually we want, right? Like we want to know, can 16 jump straight to 22? And it can't. It can't jump straight to 22. So what we actually want here is when it unwinds to 16 and 19, how do I like we get all the way to the end, right? Like we know that it gets all the way to the end once. Boom. Okay. So we know it gets all the way to the end. Then what does it do? Count equals 1, goes on to J, plus equals 1, which would be 12. And then it ends because J does not equal numbers.count, right? J does not equal numbers.count. So it didn't make it to the end. It realized it can't move forward. So we actually should know that at this point, we can end, right? Because we're cruising along. We see that, what did it just try to compare? PO numbers sub I, PO numbers sub J. Oh gosh. Numbers sub J, 22. It just tried to compare those. It knows that that is not a jump it can make. It should just give up. It should just give up. Which then should cause it to just skip the rest of this and stop thrashing around so much. So I would hope that then it immediately goes 1, 4, 5, 6, 7, 10, 12, better, 15, 16, 19, 22. Okay, that's much better. Look at that much shorter list. Okay, holy cow, that was the problem the whole time was the condition for the loop has been correct the whole time. But the problem is that in this case, that is success. This case, this is failure. In this case, we're done counting because we succeeded. And in this case, we need to stop because we failed. Okay. So then the actual output for this whole thing is 8, which is 8. I don't need the already visited. I don't need to print out these, but I should end up with just a nice clean. I still don't have the 0 in there, but that's fine. Okay, that's fine. Let's try it. In total, this set contains, let's make sure that, because I've already struggled so much, let's make sure that we both of our sample inputs actually work and give the correct answer. And then I'm going to pull out the prints because print statements are actually they can be slow. And we don't need them. 19,208. 19,208. Okay, let's pull out the print because we absolutely don't need that. And then let's grab our actual puzzle input here, and let's try it with the real deal. Still thinking 100% CPU. Memory impact is high. Energy impact is high. Still churning. Is it literally going to be trillions? I can hear, I don't know if you can hear this, but the fans on the MacBook are starting to kick on. We can pause it and see. Yep, still cruising, and it gets deep apparently. I can only imagine how much worse this would have been with the previous algorithm where it wasn't bailing. So the previous algorithm where it did not have this, not only was it giving us the incorrect answer because it was hitting the count too many times, but also it was just looping unnecessarily. So this dramatically decreases the amount of looping that needs to happen, because at each jump, if it fails, we just bail out. So it saves us, for each miss, it saves us a couple loops, which, that's meaningful. Okay, so the fan's getting hot. And this is what I was afraid of, is that there literally would be trillions of combinations, because even if we can handle counting to a trillion, that's a lot of time for the CPU to run. So the question is, how do we make this more efficient? And I'm not sure what the answer is, so to be clear about this, walking through the array the first time is right, I think. I don't think there's anything I can do better there. You have a complete list. But you still have to step back out 1 and see if it can, or step back out 2, sorry, and see if it can jump ahead. So you still have to step back out for each combination and see if it can jump forward. I guess technically what I could do is I could build a set of just can it jump ahead, yes or no, or to which ones can it jump ahead to, and then just count the number of